Okay guys, in section 1.2 we're going to be learning about math patterns. There are a few main things I want you to take away from this lesson. You're going to learn about the recursive formula, learn what a sequence and infinite sequence is, learn about the point of ellipsis, you'll learn the difference between an arithmetic sequence and geometric sequence, and learn sequence notation. Let's start off with sequences. A sequence is an ordered list of numbers, and each number is referred to as a term. This can be something as simple as 1, 2, 3, 4, 5. An infinite sequence is like a normal sequence, however, as the name implies, it has an infinite number of terms. This can be represented by 1, 2, 3, 4, 5, comma, dot, dot, dot. Next thing I want you guys to jot down is the point of ellipsis. The point of ellipsis indicates that the same pattern continues for an infinite number of terms. So that could be something like 2, 4, 6, 8, 10. It continues increasing by 2 and will continue so unless stated otherwise. The next thing is really important, so I'll take it slow. It's called sequence notation. These notations denote certain terms of a sequence. The first sequence term is denoted as u sub 1. The second sequence term is denoted as u sub 2. The nth term is denoted by u sub n1. The term before u sub n is u sub n minus 1. And the term before u sub n minus 1 is u sub n minus 2. And this will go on. Let's do an example. Graph the first 5 terms in the sequence 2, 5, 8, 11, and 14. Well, the first thing we can do is determine that the point of ellipsis is 3, because it keeps increasing by 3 each time. Because they say only the first 5 terms, we consider this just to be a normal arithmetic sequence. This is what the graph would look like. Because the terms are only the first 5 terms, you can set it equal to as 2 is the first term, 5 is the second term, etc. So before we go on, I want you guys to take a look at these two graphs. The one on the left, you see the arithmetic sequence. You can tell that this is an arithmetic sequence because it has more of a straight line to it. The graph on the right, this shows a geometric sequence, and you can tell that this is a geometric sequence because it has more of a curve to it. The next thing I'm going to show you guys is the recursive formula. The recursive formula is as follows. A sub n equals a sub n minus 1 plus d, which a sub n represents the total amount. A sub n minus 1 usually, and in the examples I'm going to show you, will show the starting price or the amount that you start with. And d will show the difference or the amount that these examples want to increase by. Let's do an example of this. A basketball is dropped from a height of 8 feet. It hits the floor, then bounces to 6 feet. It continues to bounce, and on each rebound, it rises 3/4 the height of the previous bounce. What would the next sequence be in the term? Well, since each rebound goes by a sequence of 3/4, you can multiply 6 by 3/4 to get the next rebound height of 4.5. Next, let's write a recursive formula for each bounce. You could write that as u sub n equals 3/4 times u sub n minus 1, because that is the previous term. If you wanted to make more values, you could also make a table by multiplying each rebound by 3/4. So, after the first bounce, it would be 6, multiplied by 3/4 would be 4.5, then 3.375, 2.5313, 1.98, 1.8984, 1.4238, and 1.06785. This is helpful for when you are asked to find the value of a certain term. Rick owns an automobile dealership. Last year, he spent $16,000 on advertising. He plans to increase this spending by $1,200 this year and each subsequent year. How much will Rick have spent by the 6th year? This is pretty easy. First set up your equation A sub n equals A sub n minus 1 plus 1200, because this is the amount he wants to increase by. It's pretty simple from here. If he spent $16,000 on year 1, just add $1,200 for each year. So by the second year, he would have, that's right, $17,200 spent on advertising. By year 3, $18,400, then $19,600. By year 5, he'll have spent $20,800, and by year 6, he will have spent $22,000. So your final answer is $22,000. Make sense? Alright, let's do one more example. Miss Long created an alma mater endowment starting at $250,000 and will add $50,000 to it each year. However, 25% of it will be used for scholarships. How much of the endowment will be left by the 6th year? This one is a little more difficult because you have an extra variable in the mix. Let's solve the equation anyways. A sub n equals 0.75 because you only have 75% to use since 25% is being taken for the scholarships, times A sub n minus 1 plus 50,000. Now let's solve. For year 1, use 250,000 for A sub n minus 1 because this is your original amount. Now add 50,000 to get 300,000. Now, multiply 300,000 by 0.75 because once again, we can't use all of the money because some is going to scholarships. Your answer is 225,000. So for year 1, you have $225,000 available for the endowment. Now, for year 2, take 225,000 and add 50. Once again, you multiply this by 0.75 to get 92,188. Because you have to round up the decimal. By year 4, you have 181,641. By year 5, you have 173,730. And by year 6, you have 167,798. Which is your final answer?